Hello, everyone. Welcome and thank you for joining the very last webinar of the year 2019, Interpreting Laser Diffraction Results for Non-Spherical Particles. My name is Julie Chen Nguyen, and I'm going to facilitate today. So it is my great pleasure today to introduce to you our speaker today, Dr. David Scott. David received his PhD in physics from Williams & Mary. He has 31 years of experience in R&D at DuPont as the company's leading expert in particle characterization. He's also published 3 books, 8 U.S. patents, 15 invited lectures in 7 countries, and more than 60 publications, and has developed several ISO standards. After retirement, he went straight to start a technical consulting and development company named the Advanced Particle Sensors. And so, as you can see, David comes to us with a wealth of experience from all different levels. I can't think of anyone who's more equipped to discuss this kind of controversial topic on how to measure non-spherical particles with laser diffraction than David. Okay, David, the floor is yours.
Thank you, Julie. I appreciate the opportunity to talk about this topic, and I appreciate HORIBA being so open to talking about something that's a little bit out of the usual path here. So the topic, and I hope this is what you signed up for, is interpreting laser diffraction results in the case of non-spherical particles. Before we start, I'll just see if I can make a quick plug for the company. We are a new company, a new tech company. We started about 2 years ago in Wilmington, Delaware. We're on the web at particlesci.com. The focus is particle characterization. The mission is to improve particle-based processes and products through better measurement of particle properties. The offering is the kind of thing you might expect, consulting or training, but we also do contract R&D and custom instrumentation. And we've started doing analytical services about a year ago, so we've got some capability there. And I listed some examples of recent clients. This is over the past year or so. We've had clients in these areas, and you can see the kinds of things that we've provided for them. So, moving on to the topic at hand, this is basically just a recap of what the talk is about. Particle shape is often overlooked in laser diffraction measurements, but it actually affects the results. And in fact, the laser diffraction instruments tend to report bimodal distributions for non-spherical particles, even for samples where the particles are all the same size. And what that means is that if you get a bimodal result, it's actually ambiguous unless you consider the effective shape, and we'll talk about that. If you do know the shape, and you don't have to have great detailed information about the shape, but if you do know, for instance, that it's basically spherical or not spherical, then you can resolve this ambiguity, and actually you can determine things like aspect ratio, and I'll talk about that. And then finally we'll wrap up with practical applications for measurements in various materials. This presentation is based on a paper that I gave 5 years ago in Japan, and basically I've taken a lot of the same material but expanded on it. The paper was actually only about a 20-minute conference paper, and this presentation includes a lot more detail. The outline, there must be some groans in the audience. We're going to review laser diffraction. I'm sure most of you know quite a bit about laser diffraction, but in case a few of you don't, I thought it would be good to start there. And then we'll talk about the impact of shape on the laser diffraction results. Then that will bring us to the measurement dilemma, what I'm calling the measurement dilemma, and how we resolve it. And then we'll move into interpreting the results for non-spherical particles and present the applications. Okay, laser diffraction is probably the most versatile particle size measurement technique that we have. It's fast, it's simple, it covers an extremely wide range of sizes. Some instruments can go down to 50 nanometers or thereabouts. It can go up to several millimeters, so it's actually quite a wide dynamic range. It requires very little sample. For instance, it depends on what the sample is, of course, but you might need only 1/10 of a gram of powder or 0.2 milliliters of dispersion to make a measurement. We can make measurements on dispersions. We can look at droplets and liquids. We can look at sprays. We can look at particles and solvents. You can look at online and offline and in-process applications, and these are basically off the shelf now. It's commonly used throughout industry. And the graphic there just shows you how laser diffraction really overlaps two size regimes. One is basically looking at reaching down into the nanoparticle range with dynamic light scattering. The other is sieving, which typically is looking at much larger particles. Laser diffraction spans about 5 decades of particle size. So it's a nice technique, and we want to use it whenever possible. So, as you're probably aware, when we have a laser diffraction instrument, we have particles typically flowing. Now, it could be a spray, could be powder falling in front of the instrument. But in any case, you have to have a laser passing through the particles. Let's see if this goes here. The laser, when it diffracts off these particles, you get a pattern. So you can see there's an angle theta here. This is meant to represent the polar angle. The light is scattered through various angles, collected by a lens, and then captured on a detector. And ultimately, what you end up with is, if you had a two-dimensional detector and it was infinitely large, you could get a kind of a picture that's shown here, where you see basically a circle with concentric rings around it. That's an area disk, and it basically represents the diffraction pattern for a single particle. And now the flow diagram down here is basically showing in further detail. You start with a physical particle size distribution. That means the thing that's physically there. You create this diffraction pattern, which is then interpreted by the detector geometry. So in other words, we're taking that pattern, which is shown up here, the black and white picture. That's the actual pattern. But then we're sampling it in various places with the detector geometry. We take that information and run it through a data inversion algorithm. The algorithm is based either on Fraunhofer scattering or Mies scattering model. And then finally, report a particle size distribution. So that's the way things normally work. And what you get out, of course, is a particle size distribution. We know that typically, if you have an interesting sample, it typically has a range of particle sizes, and we call that the size distribution. Laser diffraction size distributions are typically reported in terms of the particle volume. So we talk about a volume-based measurement. Particle size distribution is a mouthful, so we usually say PSD. So PSDs frequently, but not always, approximate a log normal distribution. And you've probably heard that term before. And log normal distributions can be described by a median size and a geometric standard deviation. Log normal distributions, when you plot them on a semi-log graph, they resemble a normal distribution that is plotted on linear axes. And there at the bottom, you can see it's a log normal distribution, and it looks just like kind of like a bell-shaped curve, except that the axis here is logarithmic. So that's typically what we see in the case of spherical particles. Unfortunately, or not, it's just a fact of life. The particles are often not spherical. In fact, most of the time they are not spherical, and we're always dealing in terms of approximations. So I got interested in this question many years ago when I got some samples in, and the results just didn't seem to make any sense to me until I realized that it was reflecting the shape. So what kind of shapes do we see? If you look at a clay like sepulite, it looks kind of like rods or maybe flat ribbons. Other types of clay, for instance, kaolinite, are more like flakes, and you might think of those things as discs. Working down at the bottom here, if you're dealing with E. coli, which is used quite often in biotech areas, there you're looking at something that looks closer to an ellipse. If you crystallize amino acid, this is a specific amino acid here called tyrosine, you get needle-like crystals. You can get needle-like crystals. Depending on the crystal habit, you might get other shapes. Even something as simple as polymer flakes look sort of not really flake-like. They can be more like rolled up bits of pasta or something like that. But the point is you get a wide variety of shapes, and they're not spherical. And then the question becomes, how do we make the measurements and how do we interpret the results? And so for the next minute or two, I'm going to talk about how shape affects the size of measurement and the ways in which the shape affects. The first thing is, what do we mean by size when we're talking about a non-spherical particle? The diagram at the top shows various definitions of particle size. You can have Fourier's diameter. You can look at the minor diameter, projection. There's another measurement called Martin's diameter. Most labs that I know will assume the spherical cow, and what that means is you take some funny-looking object, three-dimensional object, and you say, well, what's the equivalent spherical diameter? In other words, what's the size of the sphere that has the same volume as the particle of interest? And so you see here in the case of the cow, which is not particularly spherical, but if we have to get an answer, we might be tempted to draw a red circle like this, and that gives us a particle shown in blue. And at least we can assign a size to that. We can measure the diameter of that size, as opposed to trying to get all the different measurements that could be taken on this more complicated object. So that's the first way in which non-spherical particles differ from spherical particles is right away we're dealing with an approximation. Next, it's important to realize the diffraction pattern from things like rods or spheroids or ellipses. Ellipses is a spheroid, basically. The diffraction pattern is different than that from a sphere. And in a sense, you can just consider it as basically stretching one axis. If you take a sphere, the diffraction pattern from the sphere, and stretch that pattern, you'll get the diffraction pattern for an ellipse. The diffraction pattern from rods is a little bit different, but you can see that there's a major axis diffraction component and there's a minor axis diffraction component. And the point of this slide is to show you that unlike diffraction from a sphere, for other shapes like rods and spheroids, the intensity of the diffracted light depends upon the azimuthal angle as well as the polar angle. And so azimuthal will be moving around counterclockwise like this. And you see if you go around the spherical diffraction pattern, you can go to 12 o'clock or 6 o'clock, it looks the same. But if you look at these other diffraction patterns, the orientation of the particle actually impacts how the diffraction pattern is observed by the instrument. I give a reference here in case you want to go look at the equations. I had equations in the talk that I gave 5 years ago, but I pulled them out for this presentation. Okay, the third thing that's quite interesting and different about non-spherical particles is that when you put them into a laser diffraction instrument, and here I'm talking specifically about a suspension that you might have to dilute and then put into recirculation in your instrument, so the particles are actually recirculating through the flow cell. It turns out that typically flow cells operate in a laminar flow regime with a Reynolds number much less than 2,000. And what that means is that the velocity across the flow cell has a parabolic profile. And I've shown this in these light blue colored arrows are meant to show that the velocity is highest in the center and then tapers off as you get to the edge. And the effect of this, and this has been known for almost 100 years now, the effect of this is that the particles will align perpendicular to the laser beam. Now, they don't necessarily align in the same direction. In other words, if you have needles or cigar-shaped objects, they may not all line up in exactly the same direction, but they will all be oriented perpendicular to this laser beam. And you'll see why that's important on the next slide. When we're dealing with multiple particles, and even if we're dealing with one particle, you might end up sampling that one particle, the laser diffraction pattern. You might sample that many times during the transit of the particle through the instrument, and as it recirculates, you'll pick it up. But typically, you have thousands or hundreds of thousands or millions of particles, depending upon the particle size, flowing through the instrument. And so all of these particles have their own intrinsic laser diffraction pattern, and I've shown 4 here. So you can see these shadow images here are basically diffraction patterns. They're all for an ellipse, and because the ellipses are going to be in different orientations, they're all perpendicular to the laser beam, but they're not all necessarily in the same direction. You'll get different orientations of the diffraction pattern. Now, when you recall that we're summing up over some period of time the contributions of hundreds of thousands of these laser diffraction patterns, down here at the bottom you can see this cartoon where we've added up these 4 graphs and we get a composite which starts to look very much like a diffraction pattern for a spherical particle, but I think you can sort of see that the ring structure of this depends upon the major and the minor axes of the original particles. So what that means is that when we get to this ring detector here, where we're starting at, as we go out from the center of that detector, we're basically looking at increasing polar angle. We've already integrated over the azimuthal angle. So we're getting this sort of contributions of major and minor axes on the particle, and that gives us a pattern which is intrinsically different than the spherical pattern. So, and this is the point I wanted to make about that. This pattern it's not, there's nothing wrong with the instrumentation, that's just the way this is. In order to be able to capture all of that azimuthal data as well, you would have to redesign your system so that all of your particles were aligned in the same direction. And most instruments do not do that. Okay, what's the result? The observed diffraction signal that you obtain after integrating all of those contributions, and when I say diffraction pattern, I mean what's the intensity versus the scattering angle theta. The observed diffraction pattern cannot be described by diffraction from a single sphere. And I'm showing an example here. This is the red line is the diffraction pattern. We're showing intensity versus scattering angle, and it's the diffraction pattern for a rod, which is 5 lambda by 10 lambda. Now, lambda is the wavelength of the light, and when you're doing calculations such as this, it's quite nice to put things in terms of the wavelength of the light, because then the math becomes easier. So in these diagrams, you'll see me referring to so many wavelengths of light. So this is basically a 5 by 10 rod, and it looks very similar to the pattern for a 6 lambda sphere, but it's clearly not the same. And the way that the instrument copes with that is it reports a bimodal distribution, and I'll talk a little bit more about that in a second. But basically, you get this bimodal distribution, and that's where we start to run into a problem. This is what I'm calling the measurement dilemma. So if you're sitting there in your lab one day and someone brings you a sample, and this happens more frequently than we'd like to admit, someone brings you a sample and they drop it off, and you have no idea what it is, what the particle size is, what it's made of, or anything else. It's very tempting to just chuck this into the laser diffraction system because it does cover such a wide particle size range. And now you get this result, and you get the result shown here in the middle of the page, this bimodal distribution. Now, I think a lot of people would be tempted just to send that bimodal distribution back to the person that requested the measurement and say, here you go, here's your information. And the person that gets that information is going to look at that distribution. He's going to say, well, I don't know what to do with this, but the median size on the printout says that it's got a median of 2 microns. So the particle size is 2 microns. And the problem with that is, if you think about the impact of shape, we don't know, just looking at, if you show me this PSD without any other information about the sample, I have no idea if that PSD is giving me a bimodal distribution of spherical particles, as shown here on the left-hand side, or, as we'll see in a few slides, if it's giving me a distribution, a parent distribution from these rods. This is a dilemma because you can't look at it's physically impossible to look at this one slide and determine whether I have particles that look like this or particles that look like this. The obvious answer is to put it under a microscope, do some kind of imaging to figure out what the morphology is. But presented with this information, you don't really know. So the question is, how do we interpret PSD results for non-spherical particles? I mean, if you tell me it's spherical, then I know that I'm going with this sort of idea over here where I have a bimodal distribution and everyone's happy. But if you tell me, no, in fact, they're rods, then I'm not quite sure how to address this kind of information. So that's really the basis of the talk. How do we interpret those results? So, as I mentioned, to resolve this ambiguity, we just have to know whether or not the particles are approximately spherical. When I say approximately spherical, I mean aspect ratio is pretty close to 1, 1.1, maybe 1.2. If you get up to 1.3, 1.4, you start to see some differences in the PSDs. But certainly, if you're talking about an aspect ratio of 2, where the rod is twice as long as it is wide, then you're talking about a very different way of interpreting the results, and we'll talk about that in a second. So, how do we get this information? It can be known a priori. For instance, if you know what the crystal habit is, then you can just assert, well, I know that these crystals grow in a certain way, and you can just assert that they're non-spherical. Or you can use one of these microscopy type of approach. And if the particles are spherical, the PSD can be reported as usual. So no worries. If it isn't, if you know that you have a non-spherical particle, then what do we do? Okay, so I showed you a diffraction pattern already. I can't get a good match between the diffraction signal for a non-spherical particle and a single sphere. But if that doesn't work, we can try a mixture of two different spherical sizes. And so one sphere might represent the particle diameter, in the case of the diameter of this rod, and the other sphere might represent the length of the rod. And what we find is if you do this calculation, if you do the diffraction pattern for a combination of these two spheres, then that is shown as, it's called fit in this diagram, but that purple line is in fact a diffraction pattern for a combination of so many small diameter spheres and so many large diameter spheres, and you get a pretty good fit to the diffraction pattern. So that's in the case of this rod, but I want to know the physical size of these particles, and so how do I do that? Well, it turns out I've done quite a lot of numerical work on this. It turns out that if you repeat this calculation for a number of rods of various lengths, where I'm changing B, the length of the rod, or change A, the diameter of the rod, the numerical results report that the diameter of the large sphere, this is this big blue sphere here, is about 10% smaller than the actual rod length. In other words, if you approximate this diffraction pattern, which is what I was showing back here, if you approximate this diffraction pattern with a combination of two different spheres, what you end up with is that the diameter of this larger sphere is about 10% smaller than the actual rod length. Well, that's pretty neat. What that means is I can measure what I think that large sphere is using laser diffraction, and I will be basically 10% smaller than the physical length of the rod. It turns out you can do diffraction equivalents for spheroids as well. Here's an example where we're showing a two-sphere fit against a spheroid which is 25 lambda by 15 lambda. You can't get an infinitely accurate fit with only two spheres. You actually need a continuum of a size distribution to do that, but at least you can get a pretty good idea of approximately what the size is. And in fact, you can take this one step further and to look at, for instance, you want to estimate the aspect ratio, and these are calculations that I've made on a number of different shapes and sizes, and it turns out that the particle aspect ratio, shown at the bottom here, is actually related to the ratio of these two diameters through a power law shown here, and this appears to be universal. which is a nice result. So we can actually, and I'll show you an example in just a second in case I've lost people, but we can actually get to the length of a rod, for instance, or we can measure the aspect ratio of a rod or a spheroid. So here's what I've said so far. You can do the diffraction from mono-sized rods and spheroids. It can be approximated by combining two or more spheres. I think you can see that you'll need a range of sphere sizes if you want to approximate diffraction from polydispersed samples. And in most cases, bi-log normal distributions can be fitted to the observed data. This is quite interesting because we can use the bi-log normal distribution to deconvolve the length and width contributions. There's a lot of A's and B's floating around here. Don't get too excited about that. I think it'll be more clear as I move along. Just as a reminder, bi-log normal distribution is just the addition of two log normal distributions. So now you instead of a median size and a spread, now you have two median sizes and two logarithmic standard deviations, and also the relative contribution of the two size components. So there's 5 parameters in this fit. Okay, note, you can just, you don't even have to do the fitting. If you just want to know approximately what the aspect ratio is, you can sort of look at the first peak and the second peak, take the ratio of those two sizes, and then go back to this plot here, and you can read off an estimate for the aspect ratio. Okay, I'm going to run through a number of examples now, and these are historic. Some of these are historic samples, some of these are newer samples, but basically these are things that I've looked at one point or another and scratched my head and said, what are we trying to measure? So here is an example with sepulite, which I mentioned is a clay. It's a magnesium silicate clay. It's got fibrous structure, so it looks kind of like little pieces of tape, and it's used to reinforce nanomaterials. If you use high-power sonication, you can disperse the fibers. And what's interesting is that as you go up in sonication, as you do more and more dispersal of these fibers, that the peak that's associated with the fiber diameter becomes more prevalent. In this graph, we're starting at 10.8 joules per gram sonication energy. We're going up to 101.7 joules per gram, and that's the blue curve here. And you can see we're getting down to 0.1 microns. Actually, we're actually starting to push the limits of the laser diffraction if we keep going much further. Now here's a PSD for well-dispersed sepulite. So this was for 300 joules per gram. If you put much more power than that, you're looking at titanium because your sonic horn is falling apart. But this is the PSD that we obtained. And again, the PSD of well-dispersed sepulite, since it's essentially a one-dimensional material, it's dominated by the peak associated with the diameter. In fact, if you go and inspect Bohren and Huffman on scattering, they go through a derivation of the scattering formula, and this effect is actually predicted for infinitely long rods, that basically all the scattering comes from the diameter. So we can get the diameter of these rods. Here's some tyrosine crystals. This is this amino acid that I mentioned. This is just a sample that's recirculating through the machine. We're not trying to break it or do anything to it, but these crystals are very, very, very long, and they're thin, they're needle-like. You can break them quite easily. And what you can see, and this is one of the first, these two examples, the sepulite and the tyrosine, were the first examples that really got me interested in this effect. You can see that over time, the initial PSD has a coarse tail which extends further out than after 2 minutes of recirculation. So you can see that over time this coarse tail is coming down, but this peak here, which is sitting down around 1.5 microns, that's more or less constant. So you can see, I think, that the crystals are being broken by the pump during the recirculation, and so they're becoming shorter, and so the length is getting shorter, but we're not making the diameters any different, so the diameter stays constant. Here's a deconvolution of that same crystal data. Here again, I've taken a bimodal deconvolution, and I should say it's a bi-log normal model that I'm using. And you can see here the raw PSD, which is reported by an instrument, is shown in black. Then there's a mode A, shown in blue. There's a mode B, shown in orange. And those add up to be the bimodal fit, which is pretty much the original graph. And what this allows me to do is to basically determine what the crystal length is as a function of time. And so here, this plot, I'm just showing the length, and this is in quotes because it's an estimate, but the length in microns is decreasing as a function of time. Okay, so we're going to go to ellipsoidal particles now. The polymer flakes I showed you before, there's not much to say about it. They're kind of funny looking particles, and you can't really sieve them because they'll either block the sieve or they'll go through the sieve, but because of their shape, they're quite difficult to deal with. But they also have this nice bimodal distribution that we can apply the fit to and pull out some quantitative information. So based on this approach, we found that the median of the distribution corresponding to the width is about 143 microns, and the median corresponding to the length is about 406 microns. And if I wanted to get the aspect ratio, I would take a ratio of these two numbers and then apply that graph that I showed you earlier to get an actual aspect ratio. But this is, this is ballpark, but it's quantifiable, and you can put statistics on it. If you do a little bit more work, you can say what your confidence interval and so forth are. Now, E. coli is interesting. It works, and it works in the sense that it almost works. Sometimes it works and sometimes it doesn't work. The problem is if these particles they're breaking in two, as you see here, some of them get quite long, and then they're reproducing, and so depending upon where you catch them in their life cycle, you might see two smaller little ellipses, or you might see a longer rod. So it makes the measurement a little bit complicated, and I have to say that it's the statistics on this aren't all that great. A lot of people would look at this PSD and say that was a single mode, which would be my preference would be to call that a single mode. Statistically, though, if you fit a bimodal fit to this data and a unimodal fit to this data, you actually get a better fit with the bimodal distribution. Of course, I just heard you said, of course you will get that. But what's interesting is that if we go through this, what we'll find is that from the deconvolution, we get a length which is 0.78 microns and width of 0.52. That compares with measurements from optical microscopy of 0.94 and 0.63. The aspect ratios are very close. Now, I would say that these are a little bit too close because there was supposed to be a correction factor involved, but the point is it's giving us a result which is not bad. Yeast gives a very interesting result in that, once again, the actual yeast particle itself, maybe it's not quite elongated enough to give us a good solid bimodal distribution, but by golly, we can put one, we can fit something to it, and we get this result, and it's close to the observed value. But the thing that's really interesting about this result is there was also this other peak out here. This is the laser diffraction result, giving us a very strong peak at 1 micron. And I'm not sure what that 1 micron is. It might be scattering from the cell wall. It might be something else. Point is that when you start getting down to these fairly small aspect ratios of like 1.5 or thereabouts, it becomes harder to apply this technique. And we move on to plates. So this is kaolinite clay. You see a whole bunch of measurements there. These were taken after kaolinite was dispersed in an organic solvent at a high shear mixer, and we took the power number of the rotor in order to determine the specific energy for each sample. And so you see a whole family of curves there, and they have, very clearly a bimodal distribution there, and it's changing over time. So we do the deconvolution, and what do we see? Well, we see a peak, submicron peak, and we see a peak it's up around 5 or 6 microns in this case. So we get something that resolves quite nicely. And then if we plot the results, so what I'm doing is I'm taking these deconvolutions and I'm getting basically a centroid or a median size or a median dimension for this peak and for this peak. And of course, I'm saying that this is, in this case, this is a diameter, or in this case of a plate, this is more like a thickness, and this is more like the diameter of the plate itself. If you plot that versus specific energy, you get a very interesting result. Basically, the thickness of the plate, shown here with the blue, initially it dropped a little bit, but mostly it's steady, even as we go up to very high specific energy. But the diameter was coming down. We're not even to a grind limit yet. The diameter is still decreasing as we go up in specific energy. So what does that mean? It means that the plates, these plates of kaolinite, are breaking, but they're not exfoliating. In other words, the plates that are stuck together like a stack of cards, the cards are not coming apart, but the cards are being chopped in half by the rotor stator. So that's a nice quantitative result that we can start looking at optimizing a process. For instance, if you're trying to make a nanocomposite and you want to put a filler in there with kaolinite, you want to know, is it dispersed? How well is it dispersed? Can I drive it down further? And what this is showing you, this result, is that we are not really making it. We're not exfoliating. We're not getting the cards broken apart, but we are breaking things up. And in fact, you might not want to break them up beyond a certain limit. So that's where trying to get this kind of information from the original PSD, I think you can see there's a big difference. This looks like a mess, and you're not really sure what to say to your customer. Whereas this is a fairly straightforward story. You can say, under these conditions, at this specific energy, we can get the platelets broken down to, let's say, 3 microns, and you know exactly what it means. So the conclusions are that the laser diffraction typically will give you a bimodal results for non-spherical particles. I mean, especially where the aspect ratio is greater than roughly 1.5. I mean, there's a lot of other things in there, the index of refraction and so forth. But from this work, that appears to be roughly where we see a very distinct onset of a second peak in the apparent PSD. The second conclusion is that we can interpret multimodal PSDs only if we have a priori knowledge of particle shape, or at least we can put it under a microscope of some sort and get information about it. But we don't really need to know detailed information. So you don't need to know the actual aspect ratio. You don't need to know eccentricity or anything like that. You have to be able to get a feel for, is it mostly spherical or is it mostly cigar shaped? Thirdly, bi-log normal distributions can be fit to the PSD data for a variety of industrial particles. It doesn't work 100% of the time, but it works like 99 or 95% of the time. And if you can do that, then you can get approximate distributions of particle length and width, or of width and thickness, depending upon the geometry that you're looking at. We saw that there was a universal curve that I've discovered that shows that the true aspect ratio varies as a power of the ratio of the diameters. When I talk about the ratio of diameters here, I mean the two spheres I've used to fit to the apparent PSD. And finally, deconvolution of apparent PSD allows us to estimate aspect ratio and the true dimensions of the non-spherical particles. So here are some references that I alluded to. There are credits at the end for a couple of the images, and with that, I will take questions.
Well, thank you so much, David, for the excellent webinar. I know there's so much content and think, graphs and data that I think people might want to go back and look at. Okay, so we'll move on to the Q&A. The question here is there a single parameter that is a good indicator to distinguish the different size distribution of non-spherical particles?
Yeah, I think what came out, I think you saw it alluded to a couple of places here. If we know that the aspect ratio is larger than about 1.5, 1.5, then you know you're going to have an issue with this. If it looks like it's basically spherical, then you don't have a problem.
Okay, thank you. The second question is, we're facing issues to understand agglomerates, primary particles. Can you share the effect of external sonication on the effect of agglomeration and primary particles?
Yeah, this is a very good question because it often comes out when you're measuring particle size. What am I actually measuring? And it happened to me once. Someone gave me a sample and they said, I want you to measure the particle size on this. And so I buzzed it up and measured it and got a nice, 2-3 micron particle size and came back to me. And he was upset because he was interested in flocks. He was interested in the size of his flocks, but he hadn't told me that. And so you have to know when you're trying to understand agglomeration and flocking versus primary particles, you have to first of all define what you're interested in knowing. Are you interested in knowing the primary particle size? To some people, primary particle size means something that is like early on in the creation of the particle, but you can't actually ever see it again. A lot of people talk about aggregates, which are the smallest things you can break down to. It's a highly centered information. So when you talk about external sonication, one way to use that is to do what we call a sonication ladder, or some people call it a sonication titration, where you apply sonication under a set of standard conditions. You have to specify volume and the amount of time. You have to cool the sample and all this. But you apply sonication, and then you look at the particle size as a function of total specific energy that you put into that. And you will often see plateaus where you can kind of figure out where bonds are breaking, things like that. So careful analysis requires a lot of time. I mean, that's the trick. But first you have to define what you want. When you say agglomeration, you want to know the aggregates that are making up the agglomerates, or you want to know something else?
Thank you. Okay, and then the question just came in. Does the DLS, dynamic light scattering, also determine the particles as a spherical particle, or does this only happen in diffraction?
Oh, yeah, that's a really good question. A similar thing happens. I've seen it, but I haven't studied it. A similar phenomenon happens with dynamic light scattering because for a non-spherical particle, you have, instead of having a single diffusion coefficient corresponding to the particle diameter, now you have 2 diffusion or maybe 3 diffusion coefficients, one corresponding to the diameter, one corresponding to the length. And so the DLS will have the same issue trying to fit a single parameter particle size to something which is inherently has 2 sizes. Yeah, that's a really good question.
Thank you. Okay, and then the next question is, my sample includes different things like lipid droplets, bean flowers, and digestive enzymes. This person is actually doing a study now on how bean modulates lipid digestion. So the question is, how do I differentiate which peak from which things? I also did the optical and confocal microscopy.
Yeah, that's the usual issue. Someone gives you a multi-component sample, and you're trying to figure out how to interpret the results, because of course laser diffraction doesn't really look at, it doesn't distinguish between the components very easily. What I normally do is distinguish in terms of size regime. So if you're lucky enough to have some confocal microscopy or some other kind of size data, and you know that certain structures are a certain size, then you can probably remove that from the PSD, and basically you're trying to eliminate various things based on other pieces of information that you have. It's quite difficult to do this.
But that's the fun part.
Yeah, the other thing about that, just as a follow-up, the other thing about that question is that if you have particles which are smaller than a a few microns, and they're in the presence of particles that are bigger than a few microns, and you know that there are different things, then you run into problems with what refractive index do I use. If everything is bigger than a few microns or 5 microns or something like that, you can use Fraunhofer approximation. But if you have particles where you know that you cannot use Fraunhofer approximation, then the question becomes, what particles do I use? It's a big problem.
Thank you. I also believe that we have a applications note on bean flowers specifically. So let me send it to you offline and do a follow-up. Next question is it possible to identify a particular chemical composition or group or other information obtained from NIR spectroscopy?
The short answer is yes. You don't get the kind of quality of information that you would get from a regular infrared long wavelength spectroscopy. But I've actually used years and years ago. I built a device that distinguished different kinds of polymers for recycling based on NIR, and so I know you can do this, but it may not give you the quality of information you're looking for.
Thank you. Okay, the next one. What to do in case of sespo emulsion? I hope I pronounced it right. Spherical droplets as emulsified phase and solid crystals in the same formulation. What to do?
Yeah, it's the same problem. And again, it comes down to size. If everything's bigger than a few microns, you can at least do a Fraunhofer measurement. If, let's say, the droplets are small enough, and the droplets might be okay, but you might have very fine crystals in there where you want to use Mies scattering, and basically you have to sort of convince yourself that you've figured out one piece of it, and then consider taking, say you've got this bimodal distribution, and you've got a piece of it figured out what the size is, and now you've got to you might end up having to recalculate PSD based on a different refractive index for the other phase. But in the light of the talk that I just gave, the solid crystals, now that becomes quite interesting, because are the crystals blocky crystals? Are they plates? Are they needles? Because depending upon the morphology of those crystals, you will get either one or two peaks in your PSD, in your apparent PSD, and so you have to apply the techniques I was just talking about in order to get the crystals. The droplets are, in some sense, easier, particularly if they're bigger than several microns, because you can just use Fraunhofer on them.
And if you'd like to follow up on this question, feel free to send us, drop us a quick note at labinfo@horiba.com. Will aggregated materials get measured as a big particle?
Typically, but it depends upon the shape. So if you have a spherical aggregate, it will show up as one big particle. If you have, I'll say, an aggregate which is like fumed silica or some very open structure, some very fractal looking structure, you'll actually get some contributions from like the neck regions. So you might actually get, it might appear as a multimodal distribution. So it depends a lot on the exact shape of the aggregate. But I mean, as a general rule, if the aggregates are more or less spherical, then you should see basically one big particle.
Thank you. And because we've been talking about bimodal distribution throughout David's talk today, I want to drop a note here to let our audience know. The HORIBA LA960 laser diffraction instrument software is equipped to automatically deconvolute bimodal triple modal distribution. So essentially what I'm saying is you don't have to export that onto an Excel spreadsheet that's readily available within. Okay, and I think the very last question is, in mucilage sample, what do I have to do in order to get the right result?
Yeah, so I'm not really sure what they're trying to do. But so mucilage is a I guess they're talking about the polysaccharide. So it depends upon the size, the shape, what it's in, what answer they're trying to get. So I mean it's a very open question. But typically, say, and you could look at this as a generic question. If I have any sample, what do I have to do to get the right result? And the first question to ask is, what are you trying to do with the data? when you give an answer to the customer, what is he going to do with that, or what is she going to do with that data? And if it turns out that they're going to do nothing with the data, then don't sweat it because it doesn't matter. If it turns out that they're trying to look at growth, they're trying to grow the particles to a certain size, then it becomes a little bit more clear about what you need to do. If you don't understand the application, then it's hard to figure out how to treat the sample, because the example I used before was I treated this sample the way I would treat any sample to try to disperse it, and it turned out that the guy was not interested in dispersed particle size. He wanted to know the size of the flocks. So then we went back and measured the size of the flocks, and everything was happy. So here I don't have enough specific information to really say much more.
That's okay. I want to honor your time. I just got one more question, and then we'll end the webinar. So, do highly porous materials get recognized as multiple spheres?
So so I'm imagining the highly porous material, meaning I can maybe see through it. I mean, it depends upon the solidity of this particle. If it's got a very open, almost like a mesh kind of a network where you could actually see through it at some point, then you will certainly see the nodes, the individual nodes. But I think that the actual result that you get will depend very much on the solidity. I'm trying to remember the right word for it, but how compact this structure is. If it has a lot of open space in it, you'll see the nodes more than if it's much more closed up, because the light still has to get out of the. We're talking here about a light scattering technique, and the light still has to get out. And yeah, there are other techniques like photon migration where you don't, you can actually have something that looks opaque and still get photons through it, but that's not my sense of what the question was about. So I would say it depends very much on the openness of the structure.
Thank you. Okay, so I think that concludes all the questions. Thank you so much, David. Please don't hesitate to reach out to us again at labinfo@horiba.com for any questions, remaining questions or follow-up questions that you may have. For now, have a great day, and we'll see you in 2020. Thank you so much, David.
Thank you, Julie.
All right, thanks everyone. Bye.